Hello and welcome. In this video I'll demonstrate how to perform adiabatic cooling simulations using the HVAC FEM simulator module. To do this we launch the temperature and relative humidity module. I'll use a pre-prepared calculation file for these calculations. Alright, so I'm just going to open this file. Okay. I won't go into detail describing how to fill in this data because it was discussed thoroughly in a video that's available under this button here. It's quite a long and at times boring video. However, in order to fully comprehend the proper way of inputting this particular data, I would strongly advise you to view it. Generally speaking, when it comes to the topic of adiabatic cooling itself, in order to carry out calculations here for a specific period, it is necessary to select calculations that align with the climate profile. This is the adiabatic cooling mode. We need to state the coefficient of air saturation, specifically how it's saturated with water, which is achieved within a spray chamber or some other type of structural component or device that humidifies the air using water. We generally input the dimensions of our room. Here we enter parameters for heat accumulation within the room's furnishings. We choose the location and the time frame for these calculations. Since this is adiabatic cooling, we are primarily interested in the summer period. Alright, so we're going to proceed now and input all the necessary data concerning each of the individual partitions. Now, just to clarify things, I'll explain how exactly you should interpret and define this information. Here, as you can see for the input, we only have 4 partitions to consider, which means we are essentially treating our entire room as a basic cuboid, and this approach stems from a particular simplification, which is based on the premise that if we have, for a room with a more complex geometric outline, we can find a certain simplification of this space. If we look closely, it's clear that we have this particular wall segment on the north side, and then another distinct segment also on the north side, and similarly one on the south side and another on the south. However, these sections are on the eastern side and this one is on the western. Therefore, we can make a modification where we move these fragments to the corresponding points are placed according to the correct azimuth, and we essentially obtain our simplified room diagram, which takes the form of a rectangular prism where all the internal partitions simply create for us such a clear outline. Alright, and this is where we need to input the data specifically in this field. We enter the total sum of all windows. To put it differently, if a particular partition contains a greater number of windows, then we must enter that exact quantity right here in this designated spot. And so now when it comes to adiabatic cooling itself, it is certainly a very interesting solution. It's energy efficient in many cases, but I find it very difficult to calculate. And for every designer, it poses a significant challenge to even dare to implement them in their documentation, because it's difficult to provide the kind of assurances that we can then present to the investor. Using this module, we can perform these calculations and present them in black and white to the investor, what he will have to face or what the consequences of such a system are. And decide for yourself whether we proceed in this direction or not. In my opinion, it's definitely worth it. Of course, this isn't feasible in every single building, but there's a significant number of facilities where you can genuinely and effectively enhance the microclimate conditions with a relatively modest investment. To achieve this, we also need to precisely define our heat gains and the specific supply airflow. I used the file that was previously used to simulate ventilating airflow. However, here we'll be applying an adiabatic cooling system. In adiabatic cooling, we are heavily dependent on the wet bulb temperature. What I mean is, if we take a combination of intake air as external temperature and humidity, so having a certain saturation efficiency, and then along a constant enthalpy line, we obtain a specific maximum potential for achieving supply air parameters, especially when it comes to temperature. Flaw of that kind, which is simply a characteristic that a feature of this system is introducing extra moisture to the room. That's why not every building can have such a system. However, as I said, there are many systems or facilities where this elevated relative humidity won't be a problem in any way, but rather
perhaps even say it's a necessity.
Okay, so here we have a certain pattern of heat gains, which in our facility is 50 kilowatts and is constant throughout the entire day. However, when it comes to the ventilation scheme, we will now be slightly adjusting our system. This means that during the nighttime hours, we will be using only the minimal amounts of air which are necessary for hygienic or technological requirements. However, throughout the daytime period, when we experience considerable heat gains, significant thermal gains from solar radiation and other sources, we then employ a system of intense ventilation combined with adiabatic cooling methods to effectively and truly lower the ambient temperature, the indoor spaces, and to enhance the thermal comfort for the individuals who are present within them. So I'm assuming that from midnight until 7 in the morning, we will have standard residential ventilation, and in that scenario, our adiabatic cooling system will not be functioning for us.
The seventh one too.
However, from 8 a.m. until 7 p.m., we will have adiabatic cooling, and in the later hours, there will only be purging ventilation. And for this adiabatic cooling, I am currently planning for 100,000 cubic meters per hour during these specific hours. Okay, but we confirm, and we can now proceed to initiate our calculations to thoroughly assess how the temperature within the room will develop and fluctuate, as well as the relative humidity levels inside the space. So as we can clearly see here on these presented charts, I will then proceed to the interpretation in just a moment once all of these calculations have been fully completed. This entire process should not take a significant amount of time. Okay, the calculations are now complete. I'll just zoom in on these specific peaks for a moment. So the maximum temperature that actually occurred throughout the duration of this simulation is approximately 27 degrees Celsius within the interior of the room. Considering we are utilizing only water, I believe that's a rather respectable and quite decent result. Here we have the outdoor air temperature and the supply air temperature. I'll turn off the indoor temperature to explain what each one is.
TE and TS, these are the 2 points. My apologies for the current view. I'll just zoom in a little bit closer for you to see.
And here we can observe how the difference is formed between the external temperature and the supply air temperature, which results from its passage through the spraying and humidification chamber, being de facto a direct consequence, as I previously mentioned, of the system's overall efficiency, its efficiency. The saturation of this spray chamber, as well as the theoretical maximum value we can achieve, which is the wet bulb temperature. So what we have here, you could say, is the supply air temperature that results from saturation, and this is our outdoor air temperature. So at, let's say, around 17-20 hours, the outside temperature was almost 30.5 degrees Celsius. However, the supply air temperature resulting after passing through the spray chamber is 21.6 degrees Celsius. Unfortunately, as I mentioned, adiabatic cooling has a certain disadvantage, which is a characteristic feature of this system, namely increasing relative humidity. And in our geographical latitude, or more specifically in our climate, this poses a particular problem because we can experience quite high relative humidity levels, even when employing adiabatic cooling. Nevertheless, manufacturers deal with this in various ways by implementing what's known in automation as a humidity muzzle, which effectively reduces the efficiency of the adiabatic cooling system so that the relative humidity is lowered, but then the temperature increases. These are primarily concerns related to automation solutions. However, there are numerous locations across the globe where such issues simply do not manifest themselves due to the fact that we are dealing with a dry climate where increasing the humidity levels actually helps in achieving a significantly improved indoor microclimate. Well, here in Poland, it might not always be the absolute best solution for every single type of property or site, so it's definitely not a universally applicable solution. This is certainly a good solution for a specific group of items, but not for every single one, and you simply have to keep that in the back of your mind and be aware that this is the case. If we look at the range of this relative humidity and average it out, we will typically have an average relative humidity of around 65%. However, it's known that there will be both peaks and troughs relative to these values. Here, of course, we also determine the cooling capacity balance that this system achieves, as well as the amount of water that must be supplied, delivered to the system for it to operate in the proper way. And here we see that such peak amounts are as much as about 590 liters of water per hour. Yes, and generally, when it comes to discussing these calculations here, that's everything I wanted to show you. We can modify these parameters in any way we choose, obtaining various other combinations. We can adjust and adapt it to our own specific needs. However, it is definitely a tool that allows for a truly reliable and honest the calculation of adiabatic cooling, and then together with the investor making a rational decision regarding adiabatic cooling. So I sincerely thank you for your attention, and I'll see you in the next video. Bye.